Good day. I'm Marty Alexander. I retired from the Government of Canada in November of 2010 after working for nearly 35 years as a fire behavior research officer with the Canadian Forest Service. In semi-retirement, I've worked part-time as a consultant, researcher, and volunteer. This presentation in session 2 of the Friday's Fuels Workshop series deals with the subject of computing canopy fuel load and canopy bulk density from field measurements. There are 3 objectives to this presentation. Number 1 is to point out how canopy fuel characteristics influence various aspects of crown fire behavior and conifer forests. Secondly, to explain the general processes involved in determining canopy fuel load and canopy bulk density in outdoor experimental burning studies. Thirdly, and finally, is to briefly describe the field methods involved in sampling the tree and stand structure variables used in quantifying canopy fuel characteristics. First off, it's a good idea to get familiar with some of the basic terminology and general principles involved in characterizing canopy fuels. Let's take a moment to acquaint ourselves with the terms and concepts as shown in this illustration. Consider the canopy base height and the stand height, and in turn, the live crown depth. Note that the canopy fuel load is largely represented by the needle foliage. Now the canopy bulk density represents the canopy fuel load divided by the live crown depth. Finally, as noted at the bottom, appreciate that the ladder or bridge fuels constitutes the various fuel components in the stratum between the surface fuels and the aerial or canopy fuels. We will now examine each of the canopy fuel characteristics in greater detail. The canopy base height is one of the fuel inputs used in determining whether or not a surface fire will transition to a crown fire. The other inputs being foliar moisture content and the assumption that the ladder or bridge fuels exist in sufficient quantity to intensify a surface fire. The canopy fuel load represents the quantity of oven-dry fuel per unit area that would be consumed in the overstory of a conifer forest during a crown fire. The canopy fuel load is typically expressed in kilograms per square meter. Crown fuel loads in closed forests of the boreal typically range from 3/4 of a kilogram per square meter to about 1¼ kilograms per square meter. The canopy fuel load is one of the elements used in determining a crown fire's final intensity as per Byram's I = HWR fireline intensity equation, where the W in the equation represents the amount of available fuel consumed in the entire strata of a fuel complex. The canopy bulk density represents the quantity of oven-dry fuel within a unit volume that would be consumed in the overstory of a conifer forest during a crown fire. Canopy bulk density is typically expressed in kilograms per cubic meter. A maximum canopy bulk density is typically around about 0.6 kilograms per cubic meter, and canopy bulk densities in the boreal forest generally range from 0.05 to 0.25 kilograms per cubic meter. According to Van Wagner's theory of crown fire propagation, the canopy bulk density largely determines the type of crown fire that is possible, if at all. The lower the canopy bulk density, the higher the rate of spread needed for fully developed crowning to occur. Van Wagner's simple model, represented by the curve in this graph, has been shown on the basis of experimental crown fires documented by the Canadian Forest Service between 1962 and the year 2000 to do an excellent job at distinguishing passive from active crowning. Note that the critical threshold in canopy bulk density is in the range of 0.05 to 0.1 kilograms per cubic meter. The CFIS model system for determining crown fire rate of spread is also based on the canopy bulk density, in addition to the 10-meter open wind speed and the estimated fine fuel moisture content, which is largely determined by the temperature and relative humidity of the air. To determine the canopy fuel load of a stand requires the following: the tree's stem density by diameter at breast height size class distribution based on the count trees in a stand or timber cruise. Also, a tree biomass or allometric equation based on destructive sampling relating crown foliage weight to the dBH of a tree. As shown here, the general equation for computing canopy fuel load is the summation of the crown foliage weight times the number of stems per hectare for each dBH size class divided by 10,000. The total foliage weight is divided by 10,000 in order to convert kilograms per hectare to kilograms per square meter. Note that Van Wagner assumed in his work on crown fire modeling that only needle foliage was consumed in a crown fire. The three main types of stand or timber cruise techniques are shown here. Each involves measuring count trees. You'll find that there are pros and cons to each, especially when it comes to their use in an experimental burning study. In this regard, I have found the PCQ, or point-centered quarter method, to be superior to conventional forest inventory methods. Here's a typical scene of a destructive crown fuel weight sampling. This particular case is from the International Crown Fire Modeling Experiment, or ICFME, study north of Fort Province in the Northwest Territories. Generally, 2 to 3 trees per diameter at breast height size class are sampled. The sampling process is quite simple. For a given tree, the basic steps are measure its dBH, then fell the tree, then measure its total length and live crown length, delimb the tree, separate the fuels into their various components, for example, needles, twigs, and branches by condition and diameter size class. Then obtain the fresh weights of the various components in the field. And finally, return the samples to the lab for oven drying. The equation for the ICFME site for jack pine is shown here, showing that the crown foliage weight of a tree is a function of the diameter at breast height. Note the coefficient of variation, or R squared, value is quite high at 0.88. This equation was based on sampling 33 trees with a dBH between 1.7 and 19.8 centimeters. Several similar studies have been undertaken in Canada. Arlen Johnson, for example, a University of Alberta master's student, undertook a crown fuel weight study of lodgepole pine and white spruce in Alberta back in the late 1980s. The results were published in the December 1990 issue of the Forestry Chronicle. Just a cautionary note, the use of generalized equations for estimating crown fuel weights does not take into account the fact that there are regional differences in tree species. Generalized equations appear to work well for total above ground biomass, but needles and roundwood material tend to be much more site-specific. Experimental burning studies should, wherever possible, undertake their own separate crown fuel weight sampling study. However, time and expense may dictate otherwise. A 3 to 4 person crew can typically carry out the field component of a crown fuel weight study in a week or 2 weeks, depending on the tree sizes involved. Then roughly another week for the lab work. To determine the canopy bulk density of a stand requires the following: canopy fuel load, as previously discussed, canopy base height based on a standard timber cruise and a certain number of count trees. The mean canopy base height would be, as shown here, the summation of the live crown base height measurements divided by the number of measurements. Similarly, the stand height is determined in the same manner. There are a variety of ways and instruments to measure the live crown base height and tree height of the count trees in a stand or timber cruise. A common technique involves the use of a clinometer and a measuring tape. The percent scale given on the clinometer after sighting on the point or level of interest, for example, the top of the tree or the live crown base, along with the distance to the tree, are used to compute the live crown base height and tree height, as shown in the following equation. Here's a summary of the steps involved in computing the canopy bulk density, including an actual example. Take a moment to review the steps. The live crown depth is, as previously mentioned, the stand height minus the canopy base height. The canopy bulk density is in turn the canopy fuel load divided by the live crown depth. The example is from ICFME plot 4, a more or less pure jack pine fuel complex. The number of count trees was 124. The stand height was 11.1. The canopy base height 7 meters, and the canopy fuel load 0.459 kilograms per square meter. The live crown depth is 11.1 minus 7 meters for a result of 4.1 meters. Then the canopy bulk density based on the canopy fuel load and the live crown depth was 0.11 kilograms per cubic meter. It's worth noting here that the canopy bulk density equation conforms to Van Wagner's methodology. If there appears to be significant quantities of woody fuel consumed in the canopy fuel layer, it may be necessary to undertake a post-burn crown weight sampling study. Early efforts to quantify the degree of woody fuel consumption in the canopy layer following crown fires in conifer forest involve guesstimates or assumptions, often combined with ocular estimates. Perhaps the more exacting way is to undertake a post-burn crown fuel weight sampling to determine the woody fuel consumption in the crown fuel layer. Just a brief side story here. Chris Steffner, a U of A forestry graduate who appears in these two photos, worked seasonally and part-time for me as a technician from 1995 to 2002. I often wonder if this post-burn crown weight sampling was the reason he took a permanent job in agroforestry with Agriculture Canada. As you can see, it's quite a dirty job. Another word of caution. Other methods of determining canopy base height, canopy fuel load, and canopy bulk density have been proposed by the U.S. Forest Service. But these are not compatible with Van Wagner's theory of crown fire initiation and propagation. This is a good general reference when it comes to computing canopy fuel load and canopy bulk density for experimental burning studies. One can download a copy from the Canadian Forest Service publications website. I have noted several additional readings here. One can download these publications from the Canadian Forest Service publications website and from the Crown Fire Synthesis website of the Frames homepage. I'd like to acknowledge my good friend and colleague, Miguel Cruz. He and I have worked on various aspects of canopy fuels and crown fire modeling for nearly 25 years now. This has been a brief summary on the computations involved in determining canopy fuel load and canopy bulk density from field measurements. I hope it has brought greater clarity to your understanding of these two parameters.